Good afternoon and welcome to Chegg's Live Office Hours. This is the Stoichiometry Live Office Hour. We have live office hours all week for any class you can imagine: chemistry, calculus, algebra. So I encourage you check out Chegg's social media and their website for these live office hours. My name is Allison. I'm your host. I have been a TA for regular chemistry and nursing chemistry. I've also been a student learning assistant for nursing chemistry, and then I've been a tutor for organic chemistry and then some calculus. So I love teaching, love chemistry, love math. So stoichiometry is the best of both worlds. If you're joining us for the first time today, it is so great to have you. And if you're coming back, thanks for joining again. Hopefully I can teach you something, teach you some tricks to solve these stoichiometry questions better, or just help you learn something you might not have heard of before. Throughout this live stream, I am going to encourage you to ask your own questions. I'm here to help you and personalize this live stream to you and your needs. So any questions you have, that could be from homework. It could be from something you went over in class that you're not quite sure of. Anything chemistry, stoichiometry related, shoot that at me in the chat of wherever you're streaming from, and I would be more than happy to answer that question for you. And I'm also going to start with some warm-up questions. Throughout these questions, I might ask you to interact in the chat. So before we solve the full problem, I might ask you to do some math on your own and try to beat me to solve an answer. I really encourage you to actively participate so that you can be learning or practicing whatever we're going over. But with no further ado, let's get started. So the first question is, we want to convert 0.784 kilograms to centigrams. So first question I'm going to ask you guys, remember, I want you to actively participate if you can. What conversion factors will we need for this question? Or how will we set up? So anything you can tell me about this first problem we have here, let me know. I'm going to give y'all 15 seconds. Tell me anything you would use to solve this first problem. Started us off with kind of an easy one if you've been joining the live streams for a few weeks now. But if you're new, this might be new, so it's always great to learn. So we want to convert 0.784 kilograms to centigrams. To do this, we're going to need two conversion factors. We're going to need one from kilograms to our base unit and one from our base unit to centigrams. In this case, our base unit is grams. And base unit is basically anything without a prefix. So that's grams. We can also see liters sometimes, meters. So liters, meters, grams, all different types of base units. And there's probably more. Those are just the three we'll see most commonly in stoichiometry. So our base unit is grams. So we need a conversion from kilograms to grams and a conversion from centigrams to grams. So I'm going to write these out before I set up the problem. I know 1 kilogram has 1,000 grams in it. And then I'm going to ask y'all how many centigrams are in a gram. That's better. How many centigrams are in a gram? You have 10 seconds. Let's see how well we've memorized these conversion factors. They're very important to memorize for almost any chemistry class, chemistry teacher you'll have. If your chemistry teacher gives you this, you're extremely lucky. And I wish that when I took chemistry, I was you. So, all right, if you said that 1 gram has 100 centigrams, that is correct. We don't hear about centigrams a lot, but we do hear about centimeters. So if centigrams sounds weird to you, think of centimeters and that conversion from meters to centimeters, 100 centimeters in a meter. So now we have all of our conversions together. Yes, Olimar from YouTube, 100 is absolutely correct. Great job. Now let's set this up to solve. So I always say we start with what we're given. And in this case, we are given 0.784 kilograms. What we're going to need then is a conversion. So we want to get from kilograms to centigrams. With each step we take, we want to get closer to that centigrams. So I'm going to put kilograms in the bottom and grams at the top. and then I'm going to fill in those conversions. So I know 1 kilogram has 1,000 grams. And I just got these numbers from that conversion factor that we wrote out earlier. Now, I'm going to give y'all, this is a little bit of a challenge question. Does anyone know why we put kilograms at the bottom in this case and why we didn't put grams at the bottom of our conversion factor? Does anyone know? I'm going to give y'all 20 seconds. Tell me, why do we put kilograms at the bottom and not grams? This is something important to know so that you always get it right on tests, quizzes, homework when this comes up. About 5 more seconds. Why do we put kilograms and not grams at the bottom? 3, 2, 1. Okay, so this goes back to algebra, and algebra and chemistry and stoichiometry, they all go super hand in hand. So in algebra, whatever's on the top of a fraction goes on the bottom to cancel it out. So in this case, if we want to cancel out our units of kilograms, we also have to put kilograms at the bottom. So I'm just going to cross both of these out to demonstrate that by putting that on the top and bottom, we canceled out kilograms, and now our units are grams. But we're not done yet because the problem asks for centigrams. So we need one final conversion to get from grams to centigrams. And we wrote out that conversion already, just like Olimar on YouTube said, 1 gram is 100 centigrams. So now what I want to do is put that in my calculator to figure out how many centigrams are in 0.784 kilograms. And the reason I set it up this way, this is how I was taught, and I always think it's the easiest. I've had multiple teachers teach this. I think this is the easiest. You multiply everything across the top and you divide everything across the bottom. So in my calculator, I would put 0.784 times 1,000 times 100. Since everything's on the top, I just multiply straight across. So I'm going to give you guys 30 seconds. Put that in your calculator. Let me know what you get as the answer. See if you can beat me to solving this. Got about 30 seconds. All right, about 15 seconds, guys. Beat me to getting that answer. I know you all can do it. All right, 5, 4, 3, 2, 1. Okay, if you said 78,400 centigrams, you are absolutely correct. Great job, guys. That is the answer to this first question, has the correct significant figures. If you have any questions on how we got to that answer, let me know in the chat of wherever you're streaming from, whether that be YouTube or Twitch. Let me know. If you're just now joining our live stream, it is so great to have you. I'm Allison. I am your host for this evening. And Chegg was so great as to put these live office hours together for us throughout this live stream. I encourage you, ask your own questions, ask homework questions, things you went over in class. I am here to personalize this live stream to you. We don't have to do any more of my questions if we have enough questions come in from you guys. So any questions you have, type those in the chat and I will help you learn and solve them. All right. Next, we have another little warm-up question. True stoichiometry right here. Convert 34 grams of nitrogen to molecules of nitrogen. This one's a little bit trickier than our first question, but I still think we all can do this. So I'm going to give you all 30 seconds. What conversion factors are we going to need? How would you set up this problem? You have 30 seconds. Tell me what you would do. Start now. So what conversion factors are you going to need to get from grams to molecules? And how would you set up this problem? You can kind of take inspiration from what we did in that first problem if you're a little bit confused, but I'm really going to encourage you to try to beat me to solving this one. All right, so we're going to need 2 conversions in this problem. We're going to need a grams to moles conversion, or a moles to grams, and then a moles to molecules. I drew out this chart a few weeks ago, so I won't draw it out again unless we have a request for it. But basically, the point of the chart is if you want to get from grams to molecules, grams to atoms, anything like that, you always have to go through moles first. So we need these two conversions. Grams to moles, that is going to be the molar mass of nitrogen. So if you said that, great job. You're absolutely correct. We have 1 mole of N equals 14.01 grams of N. And if you're like, what in the world, Allison, where did you get that conversion from? I got that conversion from the periodic table. So that number with the element that has the decimal points, that is your molar mass. It's your best friend whenever you need to get from grams to molecules, anything like that. Definitely get comfortable, get familiar with those molar masses. Now we need a conversion from moles to molecules. This is a bit weirder of a number. Most people still have to memorize it, so I do encourage you memorize this number if you can. But we want the conversion from moles to molecules. That is Avogadro's number. I'm guessing Avogadro is the person who discovered this number, although I don't know how, but I would be very interested to learn. But basically, we say 1 mole has 6.02 times 10 to the 23rd molecules. Again, I'm sure it took a lot of experimenting to come up with this number, but I don't exactly know how they got it. I just know it's one of the most important numbers for chemistry and for stoichiometry. So get it in your brain and you will be good. All right. Now we need to actually solve the problem. We have these conversion factors, but we haven't really converted anything. So we want to get from 34 grams. So I picked 34 grams because that's what we start with. You start with what you're given. You're given 34 grams. Then I want to get to molecules. So if we put these kind of puzzle pieces together of the two conversions that we did, we're going to figure out that we need to go from grams to moles to molecules. That's how we're going to get from grams to molecules. Going to moles is that middle ground. So grams are going to go on the bottom because just like we talked about in the question above, what's on top has to cancel out with what's on the bottom. And then we found that conversion factor and we know 1 mole has 14.01 grams of N. Now we want to get to molecules. Moles are going to go on the bottom again to cancel out moles because we want molecules as the final units in our answer. Molecules is abbreviated by MOLEC so that I don't have to write it out the whole time. But we have 1 mole is 6.02 times 10 to the 23rd molecules. So I'm going to give you guys 1 minute. Put this in your calculator. Let me know what you get for the answer. Try to beat me to solving it for that 1 minute. So 1 minute starts now. All right, about 30 seconds, guys. What is that final answer? See if you can beat me to solving it. All right, 15 seconds. Who is going to beat me? 5, 4, 3, 2, 1. All right. If you got 1.46 times 10 to the 24th molecules, you are correct. That is how many molecules are in 34 grams of nitrogen. That's a lot of molecules, but that number should make sense to us because we know molecules are super, super tiny little things. Same with atoms. This would be the same number of atoms. So atoms and molecules, super tiny. So it makes sense that 34 grams of nitrogen would have this many molecules in it. I encourage you, like, as you solve chemistry problems, to always think, would this logically make sense? And if it logically makes sense to you, there's a good shot that you are on the right track to solving that problem. So that's the end of our second question. If you're just now joining us, hi, I'm Allison. I'm hosting Chegg's Stoichiometry Office Hours for tonight. It is so great to have you. Throughout this live stream, ask any questions that you have, anything that you have in your homework you're not sure of, anything you went over in class, ask that. I'd be more than happy to help you. But it is so great to have you. And let's go on to the third problem. So this one, we've done a little work with balancing chemical equations in the past, but I wanted to do kind of a challenge problem that's not as straightforward. So I'm going to first give y'all 45 seconds to tell me what the products of this chemical equation are going to be. This is a little double replacement reaction if you've been over types of chemical equations. So you've got about 30 seconds. Tell me, what are the products of this chemical reaction? All right, 15 seconds. What are the products? Anybody know? This is a little tough. All right, 5, 4, 3, 2, 1. So we know that in the end, the cation, which is Na, cation means positive charge, is going to bond with the anion in the other compound. And the anion is going to bond, oops, that was a little too long. Anion is going to bond with the cation of the other compound. But this has a few different charges. So I think for the purpose of this problem, it's going to be easiest to write out each individual thing in its charge. So Na has a plus charge. I'm getting these all from looking at the column that it is in the periodic table. And then this PO is going to have a 3, -4 charge. I can kind of determine that by looking at the compound and seeing where the prefixes cross, or not the prefixes, but the little things in the top right corner, where they cross. I can tell that that number should be 3, or the reason I know it is I've memorized a list of polyatomic ions that most chemistry professors will require. So that's where I got that from. But the other ones are straight from the periodic table. So Mg2 plus Cl minus. So we're going to cross them. We wrote our arrows. So we yield NaCl because of this forms with this. And then we're going to have plus MgP O4. Then we want to cross these charges. So it's actually going to be Mg3PO4 2. That is a fun one. But again, the reason I have those suffixes of 3 and 2 is I crossed those charges, so they each went to the opposite element in the compound. Next, I want to actually balance this equation. So I'm going to try to clean this up a little bit so it's easier for us to kind of tell what we're looking at. All right, but now let's solve and balance. So we've got our products. You've got 30 seconds. What are going to be the coefficients for this chemical equation? 30 seconds starts now. All right, 15 seconds, guys. Five, 4, 3, 2, 1. Okay, first thing I'm looking at, I'm going to just go left to right. I have 3 NAs over here, so I have to have 3 NAs right there. So I'm immediately putting a 3 there. PO4, I have 1 here, but I have 2 over here. So automatically I'm putting a 2 here. But if I go back now, since I have 2 Na3s, I need 6 NaCls to get those NAs to match up. I'm going to move through this pretty fast. If you need me to slow down, type that in the chat and I will go slower and explain it better. So just let me know. All right. Now we have our NAs and our PO4s matching. Let's look at Mg. We have 1 Mg over here, but 3 Mgs on the right. So we're going to put that coefficient of 3. Then we have 3 Cl2s, which is 6 Cls on the left, 6 Cls on the right because there's 6 NaCl. So we have all these coefficients. I think they're right. Let's do one final check. So 2 times 3 equals 6 NAs, 6 NAs. So then we have 2 PO4s, 2 PO4s, 3 Mgs, 3 Mgs. 3 times 2 equals 6 Cls, and 6 Cls. So we know that these are the correct coefficients, 2, 3, 6, 1. If you said that, great job. I'm so proud of you, but that is how we solve that problem. So if there's any questions, I know I moved through that a little bit quickly, but I would love to slow down and go over it better. Just let me know. If you're just now joining, so great to have you. Remember, throughout this live stream, ask any questions you have about stoichiometry, chemistry, anything like that, you name it, and I want to help you learn and I will solve it for you and we can all learn together. So I encourage you to type those questions in the chat so that I can see them and help you. All right, let's move on to our next question. What is the short, long, and spin electron configuration? We've gone over electron configurations a little bit in the past few weeks, but this will be a good review, these next two problems. So I'm going to give y'all 1 minute. What is the short configuration for chlorine? Tell me the short configuration. "45 seconds." What is that short configuration? It's the easiest one to do in my opinion. About 30 seconds, guys. What is that short configuration for chlorine? And if you're not quite sure yet, don't worry. We're going to go over it in great detail. So just wait about 15 more seconds and then you'll get the whole spiel on how to do short, long, and spin electron configurations. 3, 2, 1. All right. For short configurations of something, we find that element on the periodic table. So on the periodic table, chlorine is in the third row down. To find the short configuration, first we need the previous noble gas. To find the previous noble gas, we're going to go up one row. So go up one row from chlorine and all the way to the right. And whatever element you land on, that is what you're going to start with. So for chlorine, I'm going up one row. I'm at fluorine. And then I go right all that I can. And that's the element I choose. And that element is neon. So in brackets, I'm going to put Ne for neon. And that's the first step of my short electron configuration. Then I'm going to go down to the next row. And I'm going to find what row that is. So that is row 3. So I put 3s because the s orbital always comes first. And then that is going to have an exponent of 2 because there are 2 elements before we get to chlorine. Now I'm going to go over across the row to hit aluminum. So aluminum, I count how many elements there are until chlorine. Remember, chlorine is that number, what number? 17 on the periodic table. So I'm going to go over 5 more elements. So I would put 3p5. And that is my short electron configuration. Hopefully that makes sense. If it doesn't, let me know in the chat. We'll go over it in better detail. I know that was kind of quick for if this is the first time you're seeing short electron configurations, that is a bit quick. Now, I'm going to give y'all 1 minute. Find the long configuration for chlorine. This one, since we did the short, should be a tad bit easier. But again, if this is completely new to you and you're like, I've never seen this before, Allison, don't worry. We are going to go over it in way more detail in about 40 seconds. All right. See if you can beat me before I start writing this. You've got about 25 seconds. 15 seconds. What is the long electron configuration? All right. Anybody know? 5, 4, 3, 2, 1. All right. I'm starting with that top row. There's only 2 elements in it. So that's getting 1s2. That's my s orbital going down one row. very left, I have 2 elements again, 2s2, still that s orbital. If we're needing more explanation on s, p, d, and f orbitals, let me know in the comments and I would be happy to go over it in more detail. But since we have went over this, I kind of wanted to go a little bit quickly through it. Next, going across the row, I have my p orbital, and I'm using all p6, so 2p6, second row, p orbital. Then I am going to my third row, all the way to the left, 2 elements, s orbital, 3s2, and then 3p5. And fun little fact, I can actually I'm going to show y'all, 3s2 and 3p5 go right down here. And then if you're ever like, I don't know, this is just something cool to know. Neon is whatever's left. That's the electron configuration of whatever's left. So the electron configuration of neon is 1s2, 2s2, 2p6. So that's a fun little fact if you've never known that before. I thought that was really interesting. But that's our long electron configuration. Electron is just being abbreviated by E minus. All right, last one for this problem. What is the spin electron configuration? So if you're unfamiliar with spin, that's going to use up and down arrows. If you are, though, I want to give you 1 minute to solve this problem. So 1 minute, describe how you would find the spin electron configuration. And to make it a little easier, since you can't really do arrows in the chat section, tell me how many up arrows you're going to have and how many down arrows you're going to have. And there should be 2 correct answers for this question. All right, about 40 seconds. What is that spin electron configuration? How many up arrows? How many down arrows would I have? 20 more seconds. All right, 3, 2, 1. So spin configuration, we are going to start with one line to represent our 1s orbital. As we see in this little exponent, we have an up orbital and a down orbital. Next, we are going to do our 2s up arrow, down arrow from that exponent of 2. P has 3 lines because it has 6 elements. So 2p, up arrow, up arrow, up arrow. We do all ups first, all downs second. 3s, up arrow, down arrow. Then 3p. Up arrow, up arrow, up arrow, down arrow, down arrow. That is the spin configuration for chlorine. If that makes sense, send yes in the chat. If it's still not making sense, don't worry. We're going to do another problem of electron configurations. But let me know so that I can make sure we are all learning something new, all learning something helpful that's going to grow us in our chemistry or stoichiometry knowledge. So now, if you're just now joining, welcome. It is so great to have you. We're about halfway through our live stream, so time is ticking to ask those questions. I really encourage you. Any questions you have, ask them. Type them in the chat. This can be so helpful for you. This can be your own personalized tutoring time. If you have questions, I would love to solve them for you on the board right now. But until we have a few, let's move on to some more electron configuration practice. What is the short, long, and spin configurations of titanium? You know the drill. You have 1 minute. What is the short configuration of titanium? 1 minute starts now. All right, guys, you have about 30 more seconds. Tell me, what is that short configuration for titanium? 15 seconds, guys. See if you can beat me before I put this on the board. All right, 3, 2, 1. Okay, if you have your periodic table, titanium for reference is number 22 on the periodic table. That's its atomic number, 22 protons, 22 electrons. So, first, like we did in the previous problem, we want to go up one row, which there is no like up one row in this case, so it's a little weird. But just go to that third row and go all the way to the right, and you should be at argon. So argon's like our placeholder for this. So I'm going to put AR in brackets. And then I'm just going to write the remaining electron configuration. So argon, I would go down. So I go down to 4s, 4s2, and then I count until I get to titanium. And so that would be 3d2. We have talked about this little before. D and F orbitals start numbered one lower. Don't really know why, but it's just a rule of chemistry, something to get in your brain, something to keep in mind when you're doing that homework, when you're taking those tests. So D and F orbitals start one number lower. That's why it's 3 and not 4. So we have 4s2, 3d2. That is our short configuration. That is it. Once we get to 3d2, we get to titanium. Hopefully it's making a little more sense. If it's not, that's completely fine. That's what I'm here for. Type in the chat, let me know, and I will go over this more slowly. Next, we want long configuration. So you have 1 minute. Tell me, what's the long electron configuration for this? 1 minute starts now. All right, 40 seconds. Tell me, what is that long electron configuration? Twenty more seconds. See if you can beat me to typing it. All right. 5, 4, 3, 2, 1. All right, let's write that long configuration. It's going to be very similar to what we started. Top row, left, s orbital, 1s2. Go down one row, we're at the second row. Left side, 2 elements, 2s2. Go to the right, 6 elements, 2p6. 6 elements equals p orbital. Down one more, 3s, 2, because we have those 2 elements on the left. Go to the right, have 3p6, 6 elements, all on the right side of the third row. Down one more level, and then we just use these 2 right here, 4s2, 3d2. When you can like put that short and long configuration together, it gets super easy. And like I think electron configurations are really difficult to understand at first, but the more practice you do, the more you see it in action, the more it's going to make sense. And like short, long, and spin configurations, when I first learned them, they were so confusing to me. But now I love the problems. I think they're so easy, and I think it would take a really tricky electron configuration to mess me up now. But that's our long configuration. You know the drill. You have 1 minute. What is the spin configuration for titanium? 1 minute starts now. 40 seconds, guys. Thirty or 20 seconds. 5, 4, 3, 2, 1. All right, I'm going to match it up so it's nice and easy to see. 1s orbital, 2 elements, upspin, downspin. 2s orbital, 2 elements, upspin, downspin. P orbital, so 2p, 3 lines, 6 elements, upspin, 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 downspin, downspin, downspin. 3s orbital, upspin, downspin. I'm not going to draw the line this time, but 3p orbital. Oops. 3 lines, upspin, 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 downspin, downspin, downspin. That's because that exponent is 6 arrows. 4s, upspin, downspin, exponent is 2 arrows. And last, 3d2, 1, 2, 3, 4, 5 orbitals, or 5 lines in this 3D orbital. Upspin, upspin. There are several rules like Pauli exclusion principle, off-ball principle, that say why we do 2 upspins instead of an upspin and a downspin. I don't think it's super important to understand why right now. I just think it's important to know the rules, and the rule is all upspins before downspin. So your 3D is going to have 2 upspins and not an upspin and a downspin. If you're just now joining, it is so great to have you. I'm Allison. I'm your host. Chegg was so great as to put these live stoichiometry office hours for us tonight. And they're live, which means you can have your questions answered right now. So if you're watching from Twitch or YouTube, you have a question that you're not quite sure of, or maybe you're nervous to ask, I want to tell you, I want you to ask those questions. I want to help you. This could be your time to get personalized tutoring just by typing that question in the chat bar, and I can answer it for you and help you in whatever way you need. But it's so great to have you. And let's move on until we have a few more questions. But our next question is, what's the limiting reactant if I start with 0.25 milligrams of each reactant? First step in any problem that you have in chemistry, in stoichiometry, always check to see if your equation is balanced. Always check to see if the equation is balanced. It's so important. And I can't tell you how many chemistry teachers you've had. So I'm a chemical engineering student, so I've had lots of chemistry classes. I can't tell you how many chemistry teachers I've had that have tried to trip me up by giving me a question that the equation wasn't balanced. And they got me a lot of the time. I got lots of points off on homework for not checking to see if the equation was balanced. So I'm telling you now, so you don't get those points off like me, always check to see if that equation is balanced. So the way I'd balance this is I'd have 3 C's over here. So I'd put 3 over here, 8 H's. So I'm going to put 4 H's over there. So 4 times 2 would equal 8. We have 8 H's on both sides. Then my oxygen, I have 6 plus 4. So that's 10 oxygens. So I'm going to put a 5 coefficient before that, O2, because 5 times 2 equals 10. Let's do a final check. 3 C's, 3 C's, 8 H's, 8 H's, 10 O's, 6 plus 4 is 10 O's. That is the balanced equation. Let's find that limiting reactant. I've been over this a few times, so I'm going to give y'all 1 minute. How do we find limiting reactants? What conversions are we going to need? What steps are we going to need? How do we find those limiting reactants? 1 minute starts now. All right, guys, you've got about 30 more seconds. How do we find limiting reactants? See if you can beat me before I start solving. See if you can tell me how we find limiting reactants. Such a great way to check yourself, such a great way to get practice in is just by explaining how you would solve a problem. Before I solve any problem, I always think, how would I solve this? And I come up with a plan in my head before I start actually writing on paper. So we've got about 10 more seconds to come up with a plan of how to solve a limiting reactant problem. 3, 2, 1. All right. First and foremost, we're going to need to get those milligrams to grams because we can't do much converting until we have grams. So I'm going to write out our steps. 1. So again, 1 is milligrams, 2 grams. So let's write that out. 2. We're at grams. To find limiting reactants, how we solve them is we go to moles of a product. So I'm going to do CO2 just because I see it first, but if we need to get to moles of product eventually, we're going to need to go from grams to moles. We can't go to moles of something else until we're at moles of our original element. And then third, we're going to go from moles of our reactant. I'm going to abbreviate reactant as R to moles of product. Product I'm abbreviating as P. So these are our 3 steps. So let's start by writing out, we have 0.25 mgs of C3H8 and 0.25 mgs of O2. Mg is milligram. I just find it easier to say the letters than actually say what it is, which is probably a bad habit that I need to work on. But now we're going to want to go from milligrams to grams. 10 seconds. What's that conversion factor? I know we know the milligrams to grams conversion factor. I have full faith in you guys. What is that conversion factor? 10 seconds. 3, 2, 1. Correct. It is absolutely 1 gram is 1,000 milligrams. Milligrams is going on the bottom. 1 gram of C3H8 on the top. Same with the bottom. 1,000 milligrams. 1 gram of O2, not C2. All right. Milligrams to grams is complete. We've done step 1. Now let's do step 2. We need to go from grams to moles. So grams of C3H8 to moles of C3H8. Now, how are we going to get that? Does anyone know? How do we get from grams to moles? I'm setting you guys up. You know the answer. Let me know. How do we get from grams to moles? Come on, I know y'all know. 5, 4, 3, 2, 1. Okay, we have to find the molar mass. I'm going to go super quick review of how we find molar mass. So we have 3 carbons and 8 H's in this compound of C3H8. Look at our periodic table for the individual molar mass, which is 12.01 for carbon times 3, because we have 3 moles of it. And then 1.01 for hydrogen times 8, because we have 8 moles of it. So we get 36.03 grams of carbon contributing overall and 8.08 grams of H contributing overall. And we just add that together. We get 44.11. I think that's right. It's right. 44.11 grams of C3H8 for 1 mole. So I'm just going to go ahead, copy that right over. 44.11 grams is 1 mole of C3H8. I'm going to erase this just so we have a little bit more space. And then same thing, we need to do it for the bottom. So grams of O2 to moles of O2. O2 is a super simple one. We have 2 oxygens basically. Molar mass of oxygen is 16. 2 times 16 is 32. So 32 grams per 1 mole of O2. Gonna erase that again just so we have space. Keep it nice and organized. Hopefully that quick recap of molar mass made sense. If it didn't, let me know in the chat of wherever you're streaming from, whether that be Twitch or YouTube, let me know. And I would be more than happy to go in depth. We can do multiple examples of how to do molar mass. But the last step of our limiting reactant problem is going from moles of C3H8 to moles of CO2 because CO2, moles of that was what we chose to go to as our final product. And same thing on the bottom. We need to do moles of O2 to moles of CO2. Now, does anybody know how we get from moles of that reactant to moles of that product? It's a little bit confusing, but I'm going to give you guys, 30 seconds. How do we get from moles of reactant to moles of product? 30 seconds starts now. "15 seconds, guys." 5, 4, 3, 2, 1. So if you said we use those coefficients from our balanced chemical equation, so that first step we did, hence why balancing that chemical equation is so important, we are just going to use those coefficients and balance the bottom. So for our coefficient of C3H8, we have nothing, which basically just means 1. So C3H8, we can put a 1 there. CO2, we go to the right side. We see that has a coefficient of 3. So 3 goes with CO2. Now let's look at the bottom. O2 has 5, if you see that right here. And CO2 again has 3. Now we have all this math. I'm going to give y'all, let's say 2 minutes to find both of the answers. So find how many moles of each that C3H8 and O2 create, and then find what the limiting reactant is. So y'all have a lot to do in these 2 minutes. I'll be super impressed if you can do it. You get a virtual high five if you can solve all 3 questions in the 2 minutes. Got about 1 minute and 10 seconds. I'm going to write the first answer up there, but don't look if you're solving it. Only look if you're really, really lost, and hopefully no one's too lost. But if we need to go over this in more detail, again, just let me know, and I would be more than happy to. Got about 45 more seconds, guys. Try to give me all 3 answers in this time. Putting the second answer up there. Again, don't look if you're solving. "15 seconds, guys. Three, two, one. All right. So for the first problem, for the first part of the problem, I put 0.25 milligrams of C3H8. Divided that by 1,000, divided that by 44.11, then multiplied by 3. That's what the setup of the problem basically tells me to do. And I got 1.70 times 10 to the negative fifth moles of carbon dioxide. Now, going to that second part, 0.25 milligrams of oxygen divided by 1,000 milligrams divided by 32 grams multiplied by 3 moles divided by 5 moles. Put that in the calculator, 4.69 times 10 to the negative fifth moles. Now, what is my limiting reactant? So, if you've never heard of a limiting reactant before, limiting reactants are what limits how much product we make. In most chemical reactions with 2 reactants, one reactant is going to allow us to make our product in excess, which is the excess reactant. The other is going to limit how much product we make. So logically, if we kind of think it through for a minute, we will kind of realize that limiting reactant, if it's limiting how much product it can make, whichever one of these initial compounds made less CO2, that's our limiting reactant. So 1.70 times 10 to the negative fifth is less than 4.69 times 10 to the negative fifth. So C3H8 is our limiting reactant. Hopefully that makes sense. If it doesn't, let me know, and I would be happy to go over it in more detail with you guys. But C3H8 is our limiting reactant. So we are to the last 10 minutes of our live stream. If you're just now joining, it is so great to have you. You can check out that QR code in the top left for the live streams that we're going to be having all week long. I think there's more chemistry, there's organic chemistry, there's, calculus, algebra, any of those basic, like college, basic high school classes you can think of. They're doing live office hours for. It's such a great offering. All of the office hour leaders are so insightful, know so much about their subjects. So I really encourage you to join. You can check out that QR code, check out the socials, check out Cheg's website for that information, or the website just for any help on homework that you need. But if you're just now joining, it's so great to have you. This is your last 10 minutes of this live stream to ask any questions that you have. So I encourage you, use this time wisely, use it to get your questions answered, use it as a free personal tutor. That's what I would do. But I encourage you, ask those questions. But without further ado, let's get on to this last problem, which is we've had lots of questions over ice tables and rate of reactions. So we want to know, what's the equilibrium concentration of each compound if I start with 2 grams of H2 and O2, K equals 1. This actually, I wrote this problem wrong. When we do these problems, they always have to be a molarity. So this should be 2 molarity. We're going to change that just so the problem is actually solvable. But for rate of reaction problems, we need what's called an ice table. So we first see if our equation is balanced. We have H2 on the left, and we have 2 H's on the left, 2 H's on the right. H is balanced. 2 O's on the left, 1 O on the right. O's aren't balanced. We need a coefficient of 2 here, which means we need a 2 here. One final check, 4 H's left, 4 H's right, 2 O's left, 2 O's right. So now let's put those initial concentrations down. We start with 2 molars for H2 and 2 molars for O2. Now we need the change. I'll kind of go through this a little bit quicker because we've been over it some, but change, if it's a reactant, you're thinking reactants making product. Negative sign, losing reactant to create product, so negative 2x. That 2 just comes from the coefficient. Since oxygen doesn't have a coefficient, that's just going to be minus x, because think we're losing we're losing reactant to create product. So minus sign, coefficient of 1, no coefficient in the balanced chemical equation. And then we're starting with no water, doesn't tell us we're starting with any. And we're adding 2x, we're creating product, adding product. We have that 2 there because of the coefficient in H2O. Now we just bring everything down, 2 minus 2x, 2 minus x, 2x, and we do that K equation. So K equals concentration of H2O over O2 times H2. So K is always our concentration of products over the concentration of reactants. Something pretty easy to remember after you do it a few times. But then we also, since we have coefficients, another kind of weird rule is it's the products and reactants to the exponent of the coefficient. So H2O is going to be squared because we have that coefficient of 2. H2 is going to be squared because we have that coefficient of 2. Now, let's plug in the values we got for E into that K equation. We know K is 1. So 1 equals 2x squared over 2 minus 2x squared times 2 minus x. So let's solve. We put 1, we're just going to simplify a little bit, equals 4x squared on the top. That's what 2x as a whole entity is squared. And then I'm going to do my FOIL. So 2 minus 2x times 2 minus 2x. 2 times 2 is 4 plus 4x squared minus 8x. And then I'm going to have that times 2 minus x still. Do that again at the bottom. 1 equals 4x squared. Now I'm going to FOIL all of this. So 4 times 2 is 8 plus 8x squared minus 16x minus 4x minus 4x cubed plus 8x squared. So if you have any questions on that math, I know that was a little bit fast, just doing some quick algebra, but I'd be happy to go over it in a little bit more detail. So if you have any questions, just let me know. But now we want to solve for x. So I'm going to multiply everything on the bottom over to the left side. So I'm going to get 8 plus 8x squared minus, I'm going to combine these two. Did I calculate that? Yeah, I did. Minus 20x minus 4x cubed plus 8x squared equals 4x squared. And then I can keep combining. So I have negative 4x cubed plus 16x squared. I'm just combining like terms if you've heard that language used in algebra classes that you've had before. Minus 20x plus 8 equals 4x squared. And then I want to subtract 4x squared over. So minus 4x cubed plus 12x squared minus 20x plus 8 equals 0. Now we've come to this equation. It's a little bit weird. I'm going to give you all 1 minute, brainstorm different ways of how would we solve what we're left with. So we want to figure out what x is. How are we going to solve what is left? You have 1 minute. About 30 more seconds. Ten more seconds, guys. Brainstorm ideas. How would we solve this problem? 3, 2, 1. So this is a little bit more difficult to find, obviously. The first way you could find this is by doing roots and solving for real roots of the equation. We don't have time for that tonight, but maybe next week we can do like a real roots problem and figure out the roots to solve for x. But honestly, your better options for this, and my teacher was okay with this, is putting it in a math solver. So check and help you solve this. Any math solver that you have, put it in, explore the graph. You can graph it on a graphing calculator in a test. That's what you'd probably want to do. Roots would take too long. Graph it on a graphing calculator, find that x-intercept. So in the graph, if you look at it, x is going to equal about, it looks like x equals about 0.6. Just got that from the graph. Again, that's probably your best option for doing it on a test, is graphing it in that graphing calculator. But you can also use real roots. We just don't have too much time for that tonight. But let's put x back into each of these equilibriums to get the concentration, which is what the question for. All this math just to get those concentrations. But we have x equals 0.6. And we do 2 minus 2 times 0.6 equals 0.8, because it's going to be 2 minus 1.2. Then we do over here 2 minus 0.6 equals 1.4. These are all molarities. And then we would have 2 times 0.6. It's 1.2 m. Those are all of our molarities. Hopefully that made sense. I know that was a little tough, lots of math, lots of problem to solve, but that is the last problem of our live stream tonight. It was so great to have you. I encourage you Join the live stream again next week. Same time, I'll be the instructor. And check out that QR code for all of the live stream offerings this week. Again, there's chemistry, calculus, algebra, anything you need help with, check that live stream. Thank you so much, Chuck, for hosting this, giving everyone some better learning. Come with some questions next week. I'd love to answer. Love to have you use this time as some personalized tutoring to get any questions you have answered.